All right, so this video is a bonus for the class. It's not going to be tested in any of your exams or homework, but it's basically going to give you an introduction about what if you're interested in machine learning, then what are the transferable skills from all of these econometrics things that we have learned in this class. Okay. All right, so let's get started. We're gonna talk about what we have learned about econometrics so far. And then I'm gonna compare causal questions and prediction questions. We have two major difference between a quantitative I would say if you get a quantitative question, it's either causal or prediction. Okay, so machine learning will mostly solve prediction questions. Sometimes it could also be used to solve causal questions, but that's not commonly used right now. Okay, I'm gonna talk about some basic, kind of like just give you a tool around Zoom. Okay, we talk about supervised and unsupervised machine learning, regression-based supervised machine learning, which is related to what we have learned in the econometrics class. And then how do we regulate the regression-based supervised machine learning? Okay. And then we'll talk about what next if you're interested in this field. Okay. Definitely not learning with me because I only teach you econometrics 4,000. But there are ways that you can keep pursuing if you're interested. Okay. So what have you learned about econometrics so far? For this semester, we learned these econometric models. Linear regression with one regressor. Okay, y equals to beta 0 plus beta 1 times x. And then we can have more than one regressor, which is k regressors. So we can have x1 all the way to xk. And we'll have coefficient from beta 0 all the way to beta k. Okay. We also learned nonlinear regressions, polynomials, logs, interactions, if you still remember. Okay. All right. So what do we focus on about these models? We usually focus on interpreting the coefficients. Okay. Especially the coefficient in front of the x variable of our interest. So for example, the case that we talked about many times, student-teacher ratio on test scores, we focus on beta 1, which is if we increase student-teacher ratio by 1 unit, how much units or how many units is going to change in test scores? Okay, so we think about beta 1 all the time. Sometimes it's just beta 1 itself. Sometimes we have controls. So we have beta 2 to beta k. Suppose we have k minus 1 control, different control variables. So no matter how many control variables we have, we usually don't care too much about the beta in front of the control variables because what we care most is beta 1. And my question is, why do we care about beta 1 in the first hand? That is because we need to guide a decision of policymakers whether to approve more funding to hire more teachers. Okay. So if beta 1 is negatively. If beta 1 is negatively significant, which means that if you hire more teachers, then the test scores will increase, right? Because if you hire more teachers, then student-teacher ratio will drop. And then test scores increases. Okay. So we care about beta 1 because it determines our decision. Beta 2 to beta k would not affect our decisions because we don't change the control. Our decision is to change funding to hire more teachers or not. Our decision is not about these control variables, it's about teachers. And so that is why we care about beta 1. Okay. And this is a causal question. Okay, what do we care in a causal question? We don't care about beta 0 because in some cases beta 0 doesn't even have a meaning. We don't care about beta 2 to beta k because our decision maker will not do something to do about the control variables. We usually do things about beta 1. Okay. We don't care too much about R squared and just the R squared as well. Why is that? Because we don't really need the model to fit like 100%. We don't really need to explain variation of y to the most extent, because as long as the unexplained part do not correlate with our x, then that's fine, right? Remember, omitted variable bias, right? Omitted variables affect y and at the same time correlates with our x1. If it does not, then they're fine. Okay. It still determines beta, it still determines y, but they do not correlate with x1, then we are fine leaving them out, which means that we are fine having a low R square. All right. So we don't care about all of these. We just care about beta 1. And this is a causal question, as I just said. Okay. What is a causal question? A causal question usually asks, what does X has a significant impact on Y? And if yes, then I'll increase X or decrease X. Okay. What is the prediction question? A prediction question would be like, if I tell you the value of X, can you predict Y? Okay. It's kind of like I give you a data, there's X and there's Y, you ran a regression. Now there's an extra data that comes in, and there's only X variables. There is no Y variables. I don't know the Y. Then can you predict it using the regression that you have done? That would be a prediction question. So should we hire more teachers to improve test scores? What is this question? This is a causal question. Okay. The next one is, should we approve someone's credit card application given his age and income, or her age and income? This will be a prediction question. Okay. Let me explain a little bit about why this is a prediction question. So we are actually not, we don't care about the beta in front of age and income, because we can change a person's age and income. Okay, as a credit card company, you cannot change your applicant's age. No one's age can be changed. Okay. And you cannot change your applicant's income because it's theirs. It's kind of like their life. What you're trying to predict is whether they will be able to pay their credit card. Okay. You can predict that, oh, this person will pay. Or your prediction result will be this person will likely not pay his credit card. Okay, so then if your prediction is yes, the person will pay, then you will approve this person's credit card application as a credit card company. If not, then you won't. Okay, so this is a prediction question. That is, you're not trying to change X. You are just trying to predict a Y variable. And then this Y variable's number, your predicted number, the Y hat is going to change. It's going to determine your action. All right. So we have two kind of questions. They care about different things, even though they ran the same regression. Okay. For a causal question, they care about beta 1. Okay. Is beta 1 significant? Is beta 1 does beta 1 suffer from omitted variable bias? Okay. If it does not suffer from omitted variable bias, then I believe that it is causal. Then I'll ask if it's statistically significant. If it is, then I make certain decisions. Versus a prediction question also runs a regression, but instead of asking the value of the significance of beta 1, beta 2, or whether beta 1 and beta 2 has omitted variable bias, this question actually cares about R squared and cares about y hat, which is prediction value. Okay, again, why does prediction question care about y R squared? Because I want to predict something really well to make my decisions, because the prediction results is going to determine my decision. So for example, if I'm predicting if the person will pay his credit card, if R squared is high, then I'm confident in my prediction. If R squared is low, then I'm not. And if R squared is low and if I'm not confident in my prediction, then this y hat, I don't even trust how this y hat gonna guide my business decision, right? Okay, so that is the two major difference between causal question and prediction question. Again, they both run regressions. They both run linear regressions with many regressors or one regressors, no matter what. If you have a causal question, then you ask your beta if it suffers from omitted variable bias, if not, if it's significant. If this is a prediction question, then you want a high R squared. Once you have a high R squared, then you can use a y hat to decide to determine your decision. Okay. All right. So for example, goes back to do we hire more teachers? Okay, this is a causal question. What you need to do first is do we control everything? Okay, if we have control everything that affects y and correlates with student teacher ratio, then there is no omitted variable bias. Then I can look at beta 1. Now, once everything is controlled, how much is beta 1? Is beta 1 significant? If yes, then we can hire more teachers. So we say, okay, hire more teachers does improve test scores for students. Okay, then if not, we'll say, okay, hiring teachers is not really something that makes a lot of sense. So we should spend money on something else that is more useful, right? That's how public spending works. Public spending is not like government has an unlimited amount of money. They want to make their money useful. So if it's not significant, then they don't want to spend that money. All right. How about the credit card question? This is a prediction question. You ran a regression of if the person will pay their credit card debt on their income and age. Okay. So first thing, you will look at R squared and adjusted R squared. Okay. If it's high, then income and age explains the chance of paying really well. We can trust our prediction. Okay, because R squared or adjusted R squared are high. Now the next step you would do is a new person comes in. Okay. A new person provided his income or her income and age. Of course, you won't know if this person will pay or not, okay? Because it's a new person. It's not your client yet, so there's no way you can tell if this person will be paying or not. But you can predict it using the regression we just ran, right? Using the data we ran. So you plug in this new person's income and age, you get the chance, you get a predicted y, okay. If this predicted y is close to 1, I think this should not be y hat. There should be a typo here. This should not be y hat, it should be y hat, not y, sorry. It should be y bar. Sorry, it should be y hat instead of y bar. Okay, so these are typos. Okay, predicted value is y hat. Average value is y bar. Notation. Okay, so if the prediction, which is y hat, is close to 1, then chances are high that this person will pay his credit card. That as a company, you grant this person a credit card. If not, then if it's close to 0, then we won't give it, because this regression tells you that this person's predicted chance of paying the credit card is low. So as a company, you want to avoid this kind of applicants. All right. So this is the two applications in causal and prediction questions. All right. Let's figure. I think it summarizes most of the things. Okay. Similarity is that you ran a regression for causal question, you ran a regression for prediction questions. The difference is in causal question, you have one important X that you want to change as a policymaker or a business decision maker, that you want to change that specific X and you put it in. Once you put that in, you try to figure out all the variables that you need to control to make sure this X variable is free from omitted variable bias. If this is a prediction question, then you just put any X variables there that you think will affect Y, and in whatever form. Okay, it could be polynomial, it could be just linear, it could be in log, it could be interactions. You put all the things that you think will affect or explain why, and there is none of them that is really important than the others, because you don't change X in the end. You just try to get a prediction. Okay, so then in causal question, what you care is this beta 1. You don't care about the other things. In prediction question, you don't care about the betas, okay? But you care about y hat and r squared. Okay. Again, this should be y hat instead of y bar. Yeah. This should be y hat. All right. Okay. And then at the end, it will be beta 1 that guides the decision for causal question, and it will be the y hat that guides the decision to the decision for prediction question. Okay, so the difference is which one guides the decision, right? What are the simple, what are a lot of the applications in real world or in business or in academics? I would say lots of the questions in finance. I would say most of the questions. Not just in finance, in a lot of other things are all prediction questions. Predict if someone will pay his credit card, predict the stock prices of tomorrow, all of those things. Okay, predict a picture if it's red or yellow. Predict an animal if it's a cat or dog. Okay. A lot of the policy questions are causal because you're going to change the X, and the X variable is exactly that policy. So that is why they're causal. For example, should we expand social welfare to decrease poverty? Should we expand insurance? Okay. ACA, you mark right here, right? Should we increase tax or decrease tax? Okay. All of these things are, should we change the specific X variables to affect some Y outcomes? Okay. So there are causal questions. Some questions in tech firms are also causal. So for example, Netflix will need to decide if they want to make their main page static or dynamic. Instagram wants to make a decision about whether they just make you scroll down forever instead of flipping pages, okay? So these will be X variables, okay? They want to change the X variables and they don't know which one make them more money, okay? Or which one get them more users, or which one make them more popular or more user-friendly, something like that. So the thing they want to change is the X variable. And the things they want to achieve is the Y variable. Then so now beta 1 is what they guides their decision. Okay, beta 1 is significant, it's positive, negative. Will decide if they want to use the static or dynamic matrix. Okay. All right. So that's some examples. As you can see, these are big business, and there are rich opportunities, career opportunities over there if you are into it. Okay. All right, so let's talk about machine learning. All right. This is my way of introducing you to some categories of machine learning that is kind of more related to my class. Okay. Some of them you have seen, some of them you have not seen, which is fine. Okay, so we're going to talk about it. Okay, so you probably think, what the hell is this? I'm going to explain it one by one, so don't worry about it. Okay. So first, machine learning has supervised and unsupervised, and the difference between them is whether there is a Y variable. Okay. Supervised machine learning has Y variables and X variables at the same time. Unsupervised machine learning only has X variables. Okay, so what does that mean? So supervised machine learning has at Y and X. Your Y variable can be a fruit name. Okay, is it apple? Is it banana? And your X variable is what's the color of this fruit, what's the shape, what's the taste, and then you run a regression between these. Now a new fruit come in, you don't know its name, but you use the regression you have ran to predict the name of this new fruit. Okay. So this is supervised. All of the questions we have talked about so far are supervised. Okay. So what the hell is unsupervised? What does it mean? So unsupervised machine learning only has X variables from the beginning to the end. You don't have Y variables. You don't care about Y variables. There's just X variables. And at the end, what they do is they just classify these bunch of things into different groups using X variables. Okay, so again, you have a bunch of fruits. You don't have their names and you don't care about their names. You just want to put them into different baskets. Okay, you just want to put similar things into different baskets. You just want to put similar things into the same basket. So there will be different baskets and things that are similar are together. Okay, so these are unsupervised machine learning. The technical details I'm not going to talk about, but think of YouTube videos. So YouTube has so many users. Okay, some users watch funny videos. Some users watch cat videos like me. They don't need to have any outcome that they need. They just want to classify these users into baskets. Okay. If these bunch of people watch funny videos, then we put them in a funny video basket. If these people watch cat videos, then we put them in a cat videos basket. Some of them watch news. Okay, the news basket. And what is this basket? Why is this basket useful? Okay, they're useful for recommendation. Okay, once I put you in that basket, then I recommend you new videos that the people in the same baskets watch. Okay. And so this is some kind of things like I don't need to know an outcome. There's no outcome exactly. There's just people in different baskets. And I recommend new videos that they have not watched, but people in the same basket has watched. So that's unsupervised. Okay. If you're interested, lots of things to learn. Okay. It's YouTube's algorithm is definitely much more complicated. I'm just giving you an example of it. Unsupervised is kind of one example of unsupervised machine learning is to put people into different baskets or put fruits into different baskets or whatever. All right, so back to supervised because that's what we are familiar with. Supervised machine learning try to predict y using a bunch of x. Okay, and then there is regression method, there's non-regression methods. Non-regression methods is very complicated. There's decision tree, random forest, boosting machines, vector machines, lots of things. Okay, if you don't know, that's fine. It's just important to know that there are ways to do prediction without running regressions. Okay, but we're doing something else. That's fine. Okay. No, we don't need to. Oh, this is a good example. Okay, I did put an example here. So there's classification way of doing prediction. There's also regression way of doing regression. Okay, so if a regression way of doing it, it's kind of like things that have linear or kind of like linear linear correlation, or some kind of polynomial or log or interaction, kind of like things that can be captured with all the regression, all the kind of different regression models that we have talked about. Okay, so then we can classify, we can put them in the regression side. The classification is kind of like I kind of map things that into different categories. Maybe that vocabulary is something like that. But just how about just look at these two. The green dots are y equals to 1. The blue dots are y equals to 0. We have two x variables, x1 and x2. So then we don't run a regression, we just draw a line. Okay. And we decided that if a new thing comes in, okay, if a new thing comes in, let's say this is star. If this star is in the area that I have drawn the line, if it's in the left side of the area of the line, then I predict that it's a green. It is a green thing. Okay. So then if this new thing comes in, it's a heart, and it is to the right of, or it's in the area that I decide for the blue dots, then I predict that this is a blue thing. Okay, I don't know their color. So star and heart, I know their x1 value, I know their x2 value, that's why I can put them onto this graph, but I don't know their color. And because I draw this line from my data, so that kind of like, okay, then if a new thing comes in, if it's in the green area, then I predicted it's a green. If it's a blue area, then I predict it's a blue. This is classification, or this is one way of non-regression based supervised machine learning. Okay. All right. Versus if a new thing that comes in and its x value is 80, okay, then I kind of like I can predict if it's a regression based results, then I can predict its y value, which will be around 70 or 68. Okay. So that's the difference between classic non-regression kind of style prediction or learning versus the regression type of work that we have talked mostly about in our semester. Okay. All right. So let's move on. Okay. Under the regression methods, there is with regularization and without regularization. And I'm going to explain to you by explaining what regularization is. Okay. All right. So we've seen a similar thing before. When an new x variable is added, as long as its coefficient is not 0, r squared will go up always. Okay. As long as this x variable is as long as its coefficient is not exactly 0, then r squared will go up. That means we can explain why the variation of y better. So then okay, then why don't we just find as many x variables and we can and put them all in? And the answer is it will cause overfitting. Okay. We kind of talked about this before when we talk about adjusted r squared, right? We said that, oh, if we put too many x variables in, then we should have a punishment about it. Okay. And this punishment in machine learning is represented in another way. That's kind of like, okay, how do we regularize overfitting? Okay, so without regularization means that they don't punish you. Okay. They don't punish you by putting too many x variables. And versus with regularization category, kind of like, okay, I don't want overfitting. So I'll regularize. I will punish too many x variables. Or I will punish too many useless x variables. All right. So let's take a look at overfitting. Oh, the resolution is not good. Okay, so for example, we have something that looks like a polynomial, right? If you look into the middle graph, it's a polynomial, something like that. What you want is probably like x squared, x to the power of 3 at maximum. Maybe you can have more. If you only use linear, which is an x, then it's the left graph, which shows a little bit underfitting. Okay. It fits well in the middle, but it doesn't fit well at the beginning. It doesn't fit too well at the end. You can imagine that if you predict something x is very small, then probably you're under predicting, right? And towards the end, if x is very big, probably you're also under predicting y. Okay, so that's underfitting. And what happens to overfitting? Wow, okay. Overfitting is kind of like fitting the noise at the same time. Right. That's just my favorite explanation. It's like I want to fit a general rule, but if at the same time I fit too much, I also explain too much noise, then a new thing that comes in, let's say a heart. Now let's say a star. If a new thing that comes in, and this is a star, and your prediction is here, right? Your prediction will be here because you have predict too much noise, and this star happens to not have any noise. Another thing is noise is usually random. So you don't want to predict noise. You just want to predict a general rule. So regularization is a way to prevent these things from happening. Right. So those stars should actually be here. So star, the y value of star should actually be here. But if you predict too much noise, then your prediction will go here. Versus if your star is if the star is here and your prediction is right here, and the prediction is here, then the difference between an actual and a prediction is kind of fine. Okay. All right, regularization, deal with overfitting. And now we can explain three different ways to regularize, or three different ways to punish. Okay, the names are LASSO, Ridge, Elastinet. They might have fancy names, but they just punish this coefficient in a slightly different ways. Okay. So three of them, all of them regularize coefficients, but they punish the coefficient in different ways. So remember what is OLS? OLS is ordinary least squares. And LASSO kind of like have a similar name. Okay. Not on the TV show that you watch, but it's actually called least absolute shrinkage and selection operator. This is the longer name. Okay. It also has least. Okay, ordinary least square has least, and LASSO also has a word that's least. So least means that you are trying to minimize something. Okay. If you remember what ordinary least square is trying to minimize, it is trying to minimize the sum of squares of the differences between the actual y value and the predicted y value. Or it's kind of like trying to minimize the sum of squares of the distance between that dot and the line. If you don't remember, go back to chapter 4 or 5. Okay. While this least absolute shrinkage and selection operator also minimize something, okay, and the first part is exactly the same. It's the sum of squares of the dot and of the distance between the dot and the line. Okay. But there's an extra punishment term that's called lambda times the sum of all the coefficients absolute value. So you're gonna minimize these things. So kind of like you want this term to be smaller so that you can minimize this. Okay. All right. If you love math, you can derive that, but I'm just gonna go ahead and show you what happens. Okay. So why is it called least absolute shrinkage as selection operator? So the keyword is shrinkage and selection. So some coefficients, because they're punished, so they will shrink. They're punished, so they shrink towards 0. So if they are positive, then they shrink smaller. If they are negative, then they kind of like shrink from that value to 0. So normally they become bigger, but they're just closer to 0. So they shrink towards 0, which means that some variables, if they exactly shrink to 0, so some variables will just shrink from 10 to 9, but some variables will shrink from 2 to 0. Okay, more specifically, it should be coefficients. Okay, some coefficients shrink from 10 to 9. So even though it becomes smaller, it still stays there. But if some coefficients shrinks from 2 to 0, then it becomes useless. Okay. If it's 0, then it means that this term is not useful anymore, or this x variable is not useful in the model anymore because the beta in front of it shrink all the way to 0. Then kind of like, okay, then I don't need this. I'm gonna take it away because it shrinks to 0. And so then the variables that remains non-zero, okay, the coefficients that remains non-zero, means that those variables are therefore stayed. They're remained, or they're selected as being useful. Okay. How do we explain this? Suppose, how do I explain this? Okay. Suppose beta 0 equals to, suppose without with OLS, beta 0 equals to 8, beta 1 equals to 9, beta 2 equals to 2, beta 3 equals to 1. Okay. And then with LASSO, okay, beta 0 shrink to 7. Beta 1 shrink to, let's say, 8.5. Okay. Beta 2 shrink to 0. Beta 3 shrink to 0. Okay, so what does that mean? That means that x2 and x3 is not explaining the variation in y in the LASSO regression anymore. Okay, so you can see here. You can see here all the variables, all the coefficients become smaller. Maybe I should make one of them. Oops. Maybe I should make one of them negative. Let's say this is -1. And because it shrinks to 0. Okay. Okay, so everything becomes closer to 0 or exactly 0. Okay. And then what happens? Because beta 2 and beta 3 is 0 right now. This means that in the LASSO regression, x2 and x3 is not explained. Okay, so we don't need x2 and x3 anymore, or because they are punished. So I decided that, okay, x2 and x3 are just explaining the noises here. I don't need it. I don't want it. What I need is which one? What I need is the intercept and x1. What I need is just x1. Okay. Now what? X1 is selected. So we call that shrinkage and selection operator. Okay. That's how the name comes by. Okay. All right. I think that's it. What next? Did I say machine learning mostly answer prediction questions? Okay, there is some people using machine learning to answer causal questions, but I'm not gonna cover it right now because it's just a very small bunch of people in the industry. The big question is, how do you pursue a career in machine learning if you're interested in all of the things that I just mentioned? And my answer is, it's kind of like a standard questions that we always answer ourselves. You want to do fancy things, but there are barriers to it. And the barriers are things that people don't like. Okay, including statistics or econometrics. You need to have a fundamental skills of fundamental understanding of statistics and econometrics to learn machine learning. Okay. And then you need to learn coding. Nobody does machine learning in Excel sheets. And it's going through learning, going through this kind of coding learning is something that excites you, okay, or it's something that you want to do, then that will be it. Okay. All right. That's it. Okay. So you guys this is the last session of this class. You guys are welcome to send me emails if you are interested in pursuing this. And I would suggest you to look for classes within your school to see if anything. I'm not familiar with the structure, how the school organizes different other classes that might be useful for you, or that might be I believe that people, when they learn, they should start from where they are instead of getting too far away from their comfort zone. So you should start from where you are and then taking everything step by step. And if any class is tailored to take you from here to there, or any other program is tailored to do that, that would be great. But today we live in a world that most people don't learn things because other people ask them to learn. Most people learn things because they want to learn, because they want to pursue something, so they want to learn something, and so they don't just sit there and listen to a lecture. They go out and look around and see what is suitable for their current learning plan. Okay, make their own learning plan, find their own resources. I don't see a scarcity of resources out there online for free. Some people are lazy to pay for boot camps or something like that, which is also a good way. I wouldn't say that's lazy. That's probably a good use of money because somebody gathered materials for you so that you can learn faster. But definitely everyone should be able to find useful resources, suitable resources for themselves, given their different levels and different interests. I think that is very important. And if you want to talk, you can send me an email. I will probably be back to the campus soon. A lot of classes are in person in the future. So we'll see where we get from here. Okay.